Okay, we're back. So last time I think we were talking about resonance structures, kind of where we were headed with this, I guess. And I gave you a question to think about. And I gave you three structures and said, okay, well, which of these is correct? Is it this one, this one, this one? Is it a mixture of all three, or is it none of the above? Okay. Well, when the answer is written right next to it, it's not quite as hard anymore, I guess, and not quite as much fun. But the answer is none of the above, because on a multiple choice test, the answer is always none of the above, right, when it shows up. Not always, but a lot of the time. What it actually looks like is it looks like this. Okay? Now, you might say, but that, I don't know what that means. These three are all the same anyway. What's different about this and this? Well, when you have single bonds, those are longer and they're weaker, easier to break. Double bonds are shorter and they're stronger. Get more orbital overlap, which we'll get into a little bit later. And so if nitrate actually looked like number 1, number 2, or number 3, what you would expect to see is you would expect to see a nitrate molecule have two weaker, longer nitrogen-oxygen bonds and one shorter, stronger nitrogen-oxygen double bond. And when you look at it, you actually see every single one of those bonds is exactly the same length and strength. And that's what this little dotted line means. That means it's kind of a partial bond. And these bonds are shorter and stronger than your average nitrogen-oxygen single bond, but they're longer and weaker than your average nitrogen-oxygen double bond. All right? So, we've got a problem here. Remember we talked about theories. We said theories are only good if, number 1, they make predictions. Number 2, if those predictions are testable. If you have something that predicts something that you can't even test, how are you going to tell whether it's true or not? By the way, side note, this is why Albert Einstein actually never won a Nobel Prize for general relativity. He actually won 2. It was actually for 2 other things besides that. But he never won a Nobel Prize for probably his greatest work, because when he proposed it, it just wasn't testable. How do you get something to travel at the speed of light and measure it, back in the early 1900s? And so, it wasn't until later on where we could actually test things and say, I guess he was right. But never, by that time, time had passed and he never won a Nobel Prize for it. So you have to be able to make predictions. Those predictions have to be testable, and fundamentally more important than the other two, those predictions have to come true. Okay? So we've been drawing dot structures here, and we've made a prediction. See, there ought to be one stronger, shorter nitrogen-oxygen bond and a nitrate polyatomic ion, and 2 longer, weaker nitrogen-oxygen bonds. But when you go out into the real world and you look around, you actually don't see that. You see 3 bonds that are all the same length and the same strength, and actually identical in every way. So what does that mean? What's the consequence of that? Well, when you have a theory and it makes predictions and those predictions don't come true, it means your theory is wrong. It's wrong. I mean, there's really, you could probably say it in a more polite way, but there's really no other way to say it. It's just not right. All right? So, if you have a theory that's wrong, there's 2 things you can do about this. The first thing you can do is you can get rid of your theory and come up with a better one. All right? So, imagine if you had a bucket. And your bucket, it's 1880, and you're carrying water from the well back into the house, and you've got your trusty bucket, and it's held water, for years and years and years. It's a great bucket. But one day your bucket springs a leak. Well, you've got 2 choices. One thing you can do is throw it away and get yourself a new bucket. Well, the new bucket that we're talking about here in terms of theories is something called molecular orbital theory. And molecular orbital theory it's a better bucket. It will actually predict the bond order or bond length here of these nitrogen-oxygen bonds, and it will do it perfectly, unlike Lewis dot structures. What's the problem? Well, it's a very expensive bucket. Molecular orbital theory is very difficult to understand. There are a lot of things in molecular orbital theory that are just experimentally determined. You can't calculate. It requires a lot more complex math. So it's just a more cumbersome theory to work with. We'll might touch on it a little bit in the next chapter, but we won't go very in depth. Now there are cases where you have to use molecular orbital theory. You don't have a choice. Lewis dot structures are just not going to get you there. But if you don't have to use them, it would be nice. All right? And so what do we mean by that? Well, you've got your bucket with the hole. There actually is a second possibility, and that would be patch the hole. And if you patch the hole on your bucket, you can continue to use your bucket, right? So that's exactly what we're going to do. Lewis dot structures are not perfect. You know, part of the problem, by the way, is the fact that we're drawing electrons as little tiny dots that are just kind of parked here around the atoms. Can we do that? No, we can't do that. Remember, you can only express a region of space where the electrons are most likely to be, and you can't even specify the path. But there is some truth here. Just because a theory is not perfect doesn't mean it's useful. It's very simple to use. And if I could somehow put a patch on my little Lewis dot structure theory here, maybe I can continue to still use it to make all sorts of predictions and use it in a meaningful way. All right? And that patch that we use is something called resonance theory. And it's a really good patch because, number one, it solves our problem that we're talking about here. But number two, I actually learned something extra about the molecule that I didn't know before. So it fixes my problem and tells me more information. So that's a pretty good patch. All right? So here are 5 things to know about resonance structures, what we call resonance. And they're all, equally important. But, as an author once said, some things are more equal than others. So I'll go into that as we go. But let's talk a little bit about what resonance structures are and what they mean and what you can predict from them. So to explain the fact that all 3 bonds in the nitrate ion are the same length, you invoke this concept of resonance. All right? Probably the 2 most important things to know, obviously you need to know all 5, but the 2 most important things that you need to know are, I put a little star by them for you here, okay, and they're kind of in bold, the numbers are. So the first one here is the true structure of the molecule is a hybrid, or an average of the individual resonance structures. Individual resonance structures don't exist. All right? So in other words, if I can draw 3 resonance structures here for this nitrate polyatomic ion, nitrate doesn't look like this, it doesn't look like this, and it doesn't look like this, but it actually looks like kind of an average of them. Okay, and that's what this is over here. This is something called a resonance hybrid. A hybrid is a cross. If you're in biology or something like that, you can cross a really short stemmed rose with a big flower, with a really long stemmed rose with a little tiny flower. And if you're lucky, what you'll get? Well, you'll get a really long stem with a really big flower. Now, you'll probably also get some short stems with little tiny flowers, but you can throw those away. You can keep the hybrid there that has the desirable characteristics of both, right? Well, if you think about it, you're a hybrid. Your mom and your dad got together, and we took half the DNA from mom and half the DNA from dad, and we shuffled those cards and we dealt them out, and that's what you got. Hopefully, you got a really nice set of genes from both of them. But that's what you are. You're a hybrid. You don't look exactly like your dad. You don't look exactly like your mom. People tell you, oh, you look like your mom. Well, there are certain distinguishing features of you that your mom probably has. But you don't look exactly like her. You're not an identical copy. You're somewhere in between your mom and dad, right? A little bit of both. Well, that's what the resonance hybrid is. The molecule doesn't look like this, or even a mixture of all 3. It looks like a combination. So let's take a look at this. So imagine if you had 3 parents somehow. I'm not a biologist. I don't know how that would even work, but let's just say. So here we go. We've got a single bond in this resonance structure here. Here it's a single. Here it's a double. So 2/3 of the time it's a single, 1/3 of the time it's a double, right? Okay. This bond over here is a single in this resonance structure. It's a double here, and it's a single here. So 2/3 of the time it's a single, 1/3 of the time it's a double. This bond is a double, this bond is a single, and this bond is a single. So 2/3 of the time it's a single, 1/3 of the time it's a double in my resonance structures. So do you see over here, if I took these three structures and just kind of melded them together, let's say they had a child somehow, what would it look like? Well, this bond, 2/3 of the time it's a single, 1/3 of the time it's a double. 2/3 of the time it's a single, 1/3 of the time it's a double. 2/3 of the time it's a single, 1/3 of the time it's a double. You would expect these bonds to be exactly the same length and exactly the same strength, right? And they would be longer and weaker than your average nitrogen-oxygen double bond, but they would be shorter and stronger than your average nitrogen-oxygen single bond. Would they be closer to a single bond? Would they be closer to a double bond, or would they be exactly halfway in between? Well, they would be closer to a nitrogen-oxygen single bond. Why? Because in my individual resonance structures, 2/3 of the time they're single bonds, and only 1/3 of the time they're double bonds. If half the time they were single and half the time they were double, then yeah, they'd be exactly right in between. All right? And that's what this dotted line represents. It means partial bond instead of a full double bond. Stronger than a single, but not quite as strong as a double. All right? Now, you can use molecular orbital theory on this right here. And you can calculate a bond order for these bonds here. And you will get an answer of 1.3333. Bond order 1, single bond. Bond order 2, double bond. Bond order 3, triple bond. And that's exactly what you see. So molecular orbital theory gives me the exact answer. The problem is, it's a much, much more complicated theory. When you start looking at transition metal chemistry, you have to use molecular orbital theory. You don't have a choice. And that's why you can take a nice third-year inorganic class that deals with all that stuff, and you will see molecular orbital theory in all its full glory. There are times in organic chemistry when we have to talk about molecular orbital theory, but we try to keep it to a minimum, at least at the sophomore level. Okay. Take a really fun graduate class called Physical Organic Chemistry. It's physical chemistry and organic chemistry melded together. So imagine organic chemistry with calculus. Oh, that's a fun class. Boy, I hate that class. Anyway, I get back to those here, right? So that's the first thing, and that's kind of an important thing. Your individual resonance structures don't exist. The resonance hybrid, they only suggest what the resonance hybrid looks like, and that's what actually exists. Okay? Number 2. Resonance structures are obtained by moving electrons, and that's typically the double and triple bonds. Never, ever, 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 ever move the atoms. The atoms stay the same. So let's look at our 3 resonance structures up here. So notice in all 3 of these resonance structures, my nitrogen is in the middle and my 3 oxygens are around the outside. What's really fundamentally the only difference between my 3? Well, here's my double bond here, here's my double bond here, and there's my double bond there. And that's really it. See, I just moved the double bond there. So what it kind of comes down to is this. If you see a molecule and they say, does this have any resonance structures? If it's all single bonds, don't even worry about it. Not going to have resonance structures. Are there cases where you have molecules with all single bonds where resonance structures pop up? Of course there are. There's always exceptions to the rule. You may run into those in organic chemistry someday. You won't run into those here. So, no, just don't even worry about it. If it's got double bonds or triple bonds, it might have resonance structures. If you can move that double or triple bond to a different spot here in the molecule and still get a valid Lewis-Dot structure, which really kind of goes back to number 3 here. Okay? If you move that double or triple bond and you don't have 8 electrons around the atoms and 2 electrons around the hydrogen, then yeah, not a resonance structure. So double or triple bonds suggest it might have resonance structures, but it doesn't have to. But if it's all single bonds, say no, skip that question, move on. Okay? All right, but again, never move the atoms. The framework stays the same. It's the double and triple bonds that are moving. If I had drawn something that looks like this and said, is this a resonance structure of that? Well, this is not a resonance structure because the bonding pattern is different. See, here I've got 3 nitrogen-oxygen bonds. I've got a double bond and 2 single bonds, and I got a valid Lewis-Dot structure here. But notice I got this oxygen-oxygen single bond here. So that is not a resonance structure of that. Only move the double and triple bonds when you're making resonance structures. A little bit of an oversimplification, but for general chemistry, this is perfectly fine. Okay? Is there a reason why? There is a reason why. We'll probably get to it in the next chapter as to why they don't move, but that's what you need to know. Okay? Third thing, which I kind of alluded to here a little bit earlier, resonance structures must be valid Lewis dot structures. You know, if I draw a resonance structure for something and it's got 6 electrons around a hydrogen and 4 electrons around a carbon and 16 electrons around a sulfur or something like that, not a resonance structure. Notice our resonance structures up here, they're all valid Lewis dot structures. I have 8 electrons around each oxygen and 8 electrons around the nitrogen. Okay, so if you try to move a double or triple bond and you don't get something that's valid, then you know it's not a resonance structure. If you do, then yeah, it could be a resonance structure. Okay? Now, remember we said that there are 2 things that are kind of important here. And we said that our little patch not only fixes the problem that we have, which we talked about, but I also learned something extra. And that's what number 4 is here. Resonance structures contribute extra stability to a molecule. In other words, if I can draw resonance structures for a molecule, that makes it more stable than I ordinarily would have thought it was. And generally, the more resonance structures you can draw, the more extra stability you have. Now, did I say that if I can't draw resonance structures for a molecule, it's unstable? No, I didn't say that. You know, I can't draw resonance structures for H2O, for water. Is it pretty stable? It's pretty stable. All we're saying is if I can draw resonance structures, it's more stable than I ordinarily would have thought it was going to be. All right? And the more I can draw, the more stability. The reason for this is a concept called electron delocalization. You know, when we draw Lewis dot structures, again, we draw them as little dots that kind of pull into a spot around an oxygen here and kind of park. Well, we know that's not the way electrons really look. It turns out that if you give electrons places to go, electrons don't like to be tied down. They don't like to be stuck at home in the middle of a pandemic. They like to travel. They like to go places, you know, just like humans kind of are to a certain extent. And if I can provide more places in the molecule for those electrons to go, that makes it heavier, and so therefore lower in energy, so therefore more stable. So basically what we're saying, what these 3 resonance structures are implying, is this pair of electrons right here can move from here to here to here. It has a lot of freedom of movement, and that makes the molecule more stable. How much more stable is something called the resonance energy, but it's resonance, what we call stabilization. And this becomes really important in organic chemistry, by the way. Eventually you'll see that again. But yeah, that's a big one when you're talking about resonance structures. And that's the extra thing you learn about the molecule. All right. Number 5, you can speak of major and minor resonance structures. Some resonance structures contribute more stability than others. If you run into a situation like that, the resonance hybrid looks more like the major ones and less like the minor ones. In this case, all 3 of these are equally valid resonance structures, and so therefore the molecule looks a third, a third, a third. It looks just like all 3, kind of in between. But there are cases where you run into situations where you have one really good resonance structure and maybe one not quite so good resonance structure. If that's the case, the molecule looks more like the really good one and less like the really bad one. So think of it in terms of like dominant and recessive genes or something like that if you happen to be a biology person, I guess. All right. Now, if I can draw 2 really good resonance structures for something and one just horribly, horribly unstable resonance structure, does that make the molecule unstable? No. Resonance structures only help, they don't hurt. It's just some of them don't help that much. All right. So it's like having 3 really good workers out there when you're doing something out in the field, and you got one guy that's kind of lazy, doesn't do anything. You know, well, you know, can 4 of them do more work than 3? Well, generally speaking, 4 people can do more work than 3, right? Now, we're not talking about people that do what I call negative work. You know, I've run into people that, you know, you actually spend more time fixing what they're messing up than, you know, if you just did it yourself. But, you know, we're not going there. even if they do a little bit of work, it's better than nothing, right? Well, that's kind of the way resonance structures are. And you do run into that occasionally, but probably more than likely not in this class. The more resonance structures you have, generally, the more stable the molecule is. And that's kind of the main thing you need to get out of it. Okay? So what if it were possible if you could actually hold a molecule in your hand? What if it were possible to sit there and look at a molecule and twirl it around and look at it in all its glory there? What if you could do that? What would a molecule look like? Is it possible to figure out what a molecule would look like? Yes, actually it is. Okay. This is a representation of CH4. There's my carbon in the middle, and there's my 4 hydrogens. And this is something called methane, otherwise known as natural gas. This is what's coming out of your Bunsen burner in the lab. Okay. I know you can't see it three-dimensional because, again, we're two-dimensional here again. But yeah, it actually looks like this. So imagine your Bunsen burner, and imagine the natural gas coming through the hose, and it's coming up like this. It's reacting with the oxygen, and so on and so forth. And then you get 2 side products, which I don't happen to have a model of at this point. But yeah, this is actually what it looks like. How do I know this is what it looks like? Is there any way I can kind of figure that out? Well, yes, there is. And that's where we're going next. We're going to talk about how to determine the shapes of molecules. And we're going to do it with very little math, fortunately. All right? So how do I do this? Well, what we do is we have something called the VSEPR principle. Okay? VSEPR. And that's VSEPR. What that stands for is valence shell electron pair repulsion. All right? And essentially this is what it says. Electron pairs around the central atom tend to be oriented so as to be as far away from each other as possible. Okay, so it's kind of common sense if you think about it. So let's say, for example, I've got my little molecule here. So each of these bonds, if you'll remember, is represented by a shared pair of electrons. Okay, well, electrons have a negative charge. So what do I know about like charges? Well, they repel, right? They don't attract each other, they repel. So essentially all we're saying is I've got 4 pairs of electrons around this central atom here, and those electron pairs are going to try to get away from each other. If I can get them as far away from each other as possible, that minimizes the repulsion. If I minimize the repulsion, that minimizes the energy of the entire molecule. And of course, principle of that pretty much governs all chemistry here is that atoms and molecules prefer to be in the lowest energy state possible. So if I can somehow minimize the repulsion of those electron pairs, whatever shape I end up with, that's what the molecule is going to look like 99% of the time. Does that make sense? So a fairly easy to understand concept here. When you're doing this, it is useful to be able to write something called a VSEPR formula. And it kind of takes this form right here. A, x to the m, e to the n. The A is just your central atom. There's always an A. That's not going to be the important part. X to the m is the number of shared pairs of electrons on the central atom. It's not the total number of shared pairs. You're only looking at the central atom because what's happening out here doesn't really matter. What's influencing the shape of this molecule is what's happening around this central atom. So when you're doing molecular geometry, you key in on the central atom. All right? E to the n is the number of unshared pairs on the central atom. And again, not all the unshared pairs in the entire molecule, but on the central atom. Okay? Now, there is a big chart in your book, and what I have done is I have actually made a handout for you, and that's at the end of these notes, that has all the shapes. And there's like 14 or 15 different shapes down here. Tons and tons and tons. Some of these I filled out for you. Some of them I didn't, actually. So you can go through the book, and you can actually find some examples of the rest of these, and I want you to fill in the rest. Because otherwise this video would be much, much longer than it is probably going to turn out to be anyway. All right, but all that information is in your book, so I don't feel too bad for you there. Okay, so find some examples and fill in the rest, if you possibly can. Okay. Now, you might say, do I have to memorize all these shapes and all these formulas and be able to draw this stuff? Yeah, you do. You do have to do that. But fortunately, it's not like 13 or 14 different shapes that have nothing to do with each other. All right? I'm going to give you kind of a strategy to kind of get all this to make sense. All right? It turns out that all of the shapes of these molecules tend to fall into what I call 4 families. Okay, your book will call them electronic geometries, which is probably a more scientific way to look at it. But that's the way it is. And so if you memorize the 4, 1, 2, 3, 5 main shapes in the family, then the rest of the shapes are actually derived from those 5 main shapes. All right? So what I would do is I would go about memorizing the 5 main shapes first, then you can look at the rest. All right? And so that's exactly what we're going to do. We're going to talk about the 5 main shapes first. In other words, shapes where you have no unshared pairs, just shared pairs. Then what we're going to do is we're going to come back and we're going to throw some unshared pairs in there. We're going to see how that changes things and makes them different or the same. Okay? So, guys, we've got a little handout here. I've made 3 columns for you here. We've got an example of the particular shape you're dealing with. You've got the bond angles that are associated with that shape. And you got another column over here that says hybridization. Don't worry about that column this time. Next chapter we'll talk about hybridization and how all that works. But yeah, you'll probably have an empty column here for the foreseeable future. Okay? Alright, well, might as well get started. Let's see how many of these 5 main shapes we can do. When you do this, sometimes, molecules are 3-dimensional, kind of like you and me. They're not 2-dimensional. Sometimes we start thinking of them as like flat little things on a piece of paper or on the board floating around in solution. But they're actually 3-dimensional. And sometimes that's kind of hard to see when you're dealing with a 2-dimensional plane to illustrate. And unfortunately, since you're watching this on a screen, everything I'm doing is back to 2-dimensional, so that's going to kind of defeat the purpose. But we're going to do the best we can. Chemists have molecular models, like this little guy right here. We play with toys too. It's just that, they're toys really. But what we use them for is we use them to visualize things that we can't see in our head, because sometimes it's hard to see things on a piece of paper and bring that out into the 3-dimensional world. But if you miss the 3-dimensional aspect of a molecule, it can cause you to overlook certain things. And so models help you look at a molecule and turn it around and twist it and get that in your head, the spatial characteristics of it. You can go to the bookstore, you can buy yourself a $30 molecular model set, and you can make all sorts of really pretty looking things like this. But that's probably pretty much overkill for this course. So what I have for you here is I have the world's cheapest set of molecular models. Okay, and you can get this yourself. So here's what you do. You go down to Hobby Lobby or Walmart or whatever, and you go back in the floral section, or send your girlfriend back there if you don't be seeing the floral section, and buy yourself some styrofoam balls. That look like this. And you can buy big ones, you can buy small ones. I buy the big ones so people can see, but you can buy smaller ones if you want. And then get your box of toothpicks. And then you can use the handy sack they give you at Walmart as your carrying case. And there you go. World's cheapest set of molecular models. Alright? And so in the next video, that's what we're going to do. We're going to talk about shapes of molecules, and we'll talk about the 5 main shapes. And then we'll talk about the shapes where you have unshared pairs and how that influences it. And then we'll talk about something called molecular polarity. And maybe we can get all that done in one video. I hope so, but how it goes. I kind of thought I'd get more done in this one. But we'll put that in there, and we'll talk about all that next time. So go to Walmart, get you some styrofoam balls, follow along if you would like. You can look at pictures in the book, but sometimes it's just not the same. You don't really understand trigonal bipyramidal until you actually build trigonal bipyramidal. So we'll go into that. So I guess that's probably a decent place to stop for now. So I guess we'll see you in the next video.